Hello. I thought for this video I'd maybe start with something other than a picture of my arm, as you've been getting in all the others. I've been doing some mathematical origami and I quite like these little pyramids. Just made, no glue at all. Fairly simple to fold. If I just unfold this one, you can see it's made from a square. And I am going to attach these together to form a hexagon pattern. And then I've got some more that I'm going to make into a more abstract one that I might show you another time. So there, that's exciting. I'm pleased with those. Circular motion. We have got 3 more questions to do, and this one looks a little bit intimidating, doesn't it? We've got an exciting situation in that we've got this marble track, this marble run. Vertical motion, so of course what is happening here is it's being released, it's going around this track. And at first you think, oh crikey, there's something very different happening, but the only thing that they've done is they've made this track appear here just to make the energy, conservation of energy equations just a little bit different. So rather than just equating 2 positions on the circle itself, we've got this position that's outside the circle. However, it just works exactly the same way as the others have done. When we look at the energies, I think making that level there makes sense to make that 0 level. In fact, it's it's kind of implying that as well. With that H going up there. So firstly, I'm going to start by writing down all my energies at A. So obviously H is equal to H. So gravitational potential energy plus my kinetic energy is going to be mgh plus a half m. It's being released from rest. So that is just equal to mgh. At P. So P, it's slightly more complicated. So what I'll do here is I'll just draw out my first diagram. That's shocking, isn't it? I've started the maths without drawing a diagram. So I've got that part of the circle. This is theta. I, of course, am going to be needing to work out that length there. That length there is what we need. That's my angle, theta. That is the adjacent component, so that is going to be A cos theta. I know it's A all the way from there to there. I know that that is A cos theta, so the height at P is going to be A minus A cos theta. So that makes my total energies mg multiplied by that distance plus my kinetic energy, a half mv squared. So by conservation of energy, so I'm going to equate those two. We have mgh equaling, I'm going to expand this bracket, mga minus mga, sorry, written the wrong way around, plus a half mv squared. And we're used to this by now. The m's all cancel. I'm going to make v squared the subject. I'm going to multiply everything by 2. So actually, I'm going to do that in stages. Minus 2 ga cos theta plus v squared. So v squared, I've got 2gh. That, of course, is going to be plus when I take it onto that side. And I've got minus 2ga. Okay, so now we need to focus on the circle. And as we normally do for the second step, we've got to do our resolving. We've got to use F equals ma. So I'm going to need a diagram here. So This is at position P. I've got a weight of mg. This is my angle. We've got a force here. We've got to have a force acting towards the centre of the circle, and here, of course, it's a reaction force. Normal reaction force, so this, of course, I've drawn the full circle in, but this isn't actually here, but it's travelling on the inside of this track, so that is going to be the reaction force that's keeping that in there. I'm going to be using F equals ma towards the centre in the direction of motion, all of r minus the weight component. So if I draw a right angled triangle there, that is angle theta. So this is also going to be angle theta, and you can see clearly the two similar triangles. So this is the cosine component. So that will be mg cos theta. So r minus mg cos theta is equal to mass times acceleration, mv squared over r. And we are going to be using this, so quite long, isn't it? All of that is our v squared, 2gh plus 2ga cos theta minus 2ga all over r, and the radius of that circle is a. So r minus mg cos theta equals, so I'm going to have 2mgh 2mga cos theta and 2mga, that's negative 2mga, and that's all over 8, so that is my previous line. And here, well, I've got a factor of a in there, which would cancel, but I haven't there, so I'd have to separate those first. So 2mg over a plus 2mga cos theta minus 2mga. Now those two would cancel. So r minus mg cos theta is equal to 2mgh over a, and I've got 2mg cos theta minus 2mg. Nearly there, we just need to take that onto there, and you can see I've got a 2mg cos theta. That will be an additional mg cos theta, so those will add to 3. So r is equal to 2mg over 8 plus 3mg cos theta minus 2mg, and I think that is pretty much our answer. I've just got to do a little bit of factorising there, but you can see that we're there. R is equal to mg3 cos theta minus 2 plus 2mgh over a. Okay, so the algebra there, seems a bit more complicated, but I think that is just because we started off with a slightly different thing because of the energies. We didn't start off at a point on the circle, so it led us to, I think, one more term when we're working through this R. But it's standard method, and it's something that we've done in all of the vertical questions. Okay, right, so the second part. Hence show that the marble completes the circular loop provided h is greater than 5a over 2. Okay, so we know that as we're going around here, we've got that contact happening as long as we've got normal reaction force. So when the normal reaction force reaches 0, then that's when it is going to come off. That's when it's going to fall off the inside of that track. So we know that the marble stays in contact if r stays greater than 0. So we have our previous expression. Wait, it's up here, isn't it? This is our previous expression. So r equals mg 3 cos theta minus 2 plus 2 mg h over a. R has got to be greater than theta, so this expression here has got to be greater than theta. And of course this expression here, it does contain an h, so we've got to somehow get an expression that makes h the subject of that, and an awful lot of things are going to simplify. You can see that both of those things have got an mg, so we can divide this expression through by mg. That goes. So now the only things we've got an a there, okay, and there's an a left there, but we've still got a cos theta. But if we consider this without the bracket, we'll have 3 cos theta minus 2 plus 2h over a is greater than 0. Let's make h a subject because that's what we're aiming for. So 2h over a is greater than, take that onto the side, it becomes positive, and then we've got minus 3 cos theta. And, okay, we have got multiply by a, divide by 2. So we're kind of looking like it, aren't we? We've got the a over 2. And, well, 2 minus 3. If that was 2 plus 3, we would have that 5 there. And, of course, we can think about this using trigonometry. Here is our cosine curve. And the very maximum that this expression can be is when this is down here. So this would be at -3, of course. You know that at 180 degrees, cos of 180 is equal to -1. So -3 cos 180 will be equal to +3. So it means that this will always be true when we have this particular instance here. And when theta is equal to 180, then h is greater than 2. Well, it's going to be +3, as I showed up there. A over 2. In other words, 5a over 2. So that's thinking about it in mathematical terms. But actually, many of you are probably looking at that and thinking, well, what's the point in doing that little blue section there? We know from the situation. We know from the situation that theta, remember, theta's been defined as that angle there. We know that the most extreme case is going to be at the very top. If it can make it past that top level, then, of course, it's going to stay on the inside of the track when it's beyond that very top part. So we know that the danger point, the extreme point, just happens when it's at the top. So we know that R is the most likely to fall when it's at the top. So in other words, theta is equal to 180. So you don't have to do it by, that argument by thinking about when the cosine curve is at its max or its min. We can just say, all right, it's going to be at the top, 180, and put that in there. So h would have to be greater than 2 minus 3 cos 180. And of course, we're going to get the same answer over 2. Whoops, missed off the 8. In other words, h is equal to 5a over 2. Okay, so I think it looked like a horrible situation at the start, but actually, once you get past that, it's not too bad. Okay, now onwards. Question number 10. Now, this is one where we can only do the first part. The second part, year 13. So it's a section of your mechanics that you haven't touched upon at all yet. It's a topic that's purely within year 13. And it's about when objects slide or when they topple. So part 2 we don't need to consider. The first part, however, is fair game for you lot. We have got a car travelling round a bend which is banked at a particular angle. So what I'm doing here, this is the cross section, this is the bend, but it would be kind of moving around like that. So here is the car, sorry, rubbish car, there are the 2 wheels. Because it's bending round like that, the centre of the circle is going to be in this direction here. So we have got our acceleration appearing there. We have got a radius of 100 metres. So this is 100 metres here. Forces, well, we've got the normal reaction force acting perpendicularly to the slope. So I've got those 2 forces, sorry, that reaction force is perpendicular to there. And it mentions friction. It mentions at this particular speed of 14, there's no sideways frictional force. Of course, it's that frictional force that does keep it at that level on the bank. If you can imagine, you know, if you're going really, really fast on around a bend, at some point you're going to be going too fast and you kind of slide off in that direction. So the tendency, the car will be wanting to slide up the slope. So that means that in general you would have your frictional force opposing that motion, and that's what's keeping it at that point on the bend. But of course what we're going to be saying is we're going to be saying that friction is at 0, but that is up until a speed of 14 is the direction it would be acting in, and then at 14 it would just be about to slide, and beyond 14 it would be moving up the slope. Okay, we have got a horizontal circle. Because it's a horizontal circle, we resolve and then we resolve in the opposite direction as well. So resolving, you might think, well, why don't we just kind of resolve there? What we need to do is we need to resolve in the direction of the acceleration and then perpendicularly to that as well. And I'm sure lots of you are shouting at me saying, right, you haven't got on that weight force. So I've got the weight force, the mg, acting directly down. So I have got a component of this normal reaction. I want that component up there. There is my normal reaction. That is the direction that I want the component of. That's my right angled triangle. If that angle is theta, this angle is also theta. That's my r. This is adjacent, so that is going to be r cos theta. So I have got r is equal to, no I haven't, I have got r cos theta. That is equal to, there's no frictional force at this particular point. We could of course add in a component, but I don't think there's kind of any point in that because we just know it's 0. The friction is equal to 0, so any component of that is also 0. That is just going to be equal to mg. If we now then resolve in that direction, I'm going to be using F equals ma. Of course it was in equilibrium there, which is why I can do forces up equal forces down. Here I am resolving in this direction. I'm going to have the other component of my normal reaction, that is r sine theta. I don't need to worry about the frictional force because that's 0. So I've just got that force is equal to m times by a. And because we've got speed, let's use v squared over r. R sine theta then, I don't know m. I know that v is equal to 14 and I know that r is equal to 100. So r sine theta is equal to m multiplied by 196 over 100, so 1.96. This we also know. So I need to, what do we need to work out? We need to work out the value of theta. So from that, I can say that R is equal to mg over cos theta. So that, of course, I can put into there. So mg over cos theta multiplied by sine theta is equal to 1.96 m. And m on both sides. Sine theta over cos theta makes tan. G tan theta is equal to 1.96. Tan theta is 1.96 over 9.8. And of course, you know, it's always engineered. This is just very nicely a fifth. So theta is inverse tan of 0.2, which is 11.3 degrees. Okay, and as I said, don't need to do part 2. You might be asked that in your mechanics next year, but certainly not at the moment.